Hello everyone, welcome to this video. In this video we are going to study another concept which is functions, and basically we are going to revise it in terms of abstract algebra. We are already familiar with this topic functions from our schools, right? So let's have a look and remind us what are they and how and what notations are we going to use further in this subject. So here you know what is a function. You can either call it by function or a mapping. It is basically a rule. What does it do? If you have two sets, you have a set A, you have a set B, then you take some few of the elements from this set, and then according to whatever rule that this function is defining, then this element would be mapped to some element here in this set, right? This is what it does. And what is that rule? This rule is basically it assigns each element A of A exactly one element of B. So that means you cannot have this thing that one element here is mapped to two different elements, this one and this one. This cannot be there. If this is so, then this is not a function. And if each element here, each element A of A is mapped exactly to only one element B of B, then that is a function, right? So moving further, here we call the set A, the set from which we are initially taking the elements, as the domain of that particular function. Suppose we have the mapping phi, right? For that mapping phi, the set A, this is known as the domain, and the set B, this is known as the range of the given function phi, right? And moreover, in addition, here this phi assigns B to A. So that means you are seeing, if you are having this mapping phi and you are applying it to some element A of the set capital A, then it is giving you B. So you are saying this phi assigns small b to small a. Then this B is what? It is the image of A under phi. So what is B? B is the image of the element A under phi. So this is the notation that we are going to use. And moreover, the subset B, which comprises of all the images of the elements of A, that is known as the image of the set A under phi. Now what does this mean? It means that whenever we have the set A, all the elements of this set A are mapped to some unique element here in B, right? So suppose we have three elements and all the elements, they are mapped to the elements in B. But suppose there are more elements in B which are not mapped to, which are not the pre-images of any other element. So that means only these elements are mapped under phi, and they form the image of A under phi. So that means they are left behind. So whatever is lying here within this one, you call that to be the image of A, and you see this is the subset of the set B, right? So this is the thing. Next, let us see various notations here. So here this phi double dot or colon A to B, this means that we define a mapping phi which is taking the set A to the set B, right? And in terms of elements, this is about sets, right? Whole of the, that means you are taking elements from the set A, applying phi onto it, and you are getting the image which are present in B. And how are the elements defined? Now we use the notation phi of A is equal to B to define that phi carries A to B. So it takes, or we have another notation which says that we have phi which takes the element A to the element B. This element is a part of this capital A set, and this element is a part of this capital B set, right? So this is the notation here. Now to verify that a correspondence is a function. Now mathematically, if we wanted to see, otherwise I have told you that each element of A should map exactly one element of B. So this is the definition for function. But if you are not able to see all the elements of a set, then how are you going to say that we have a well-defined function? So for that, sometimes we call this to be a well-defined property of a function, or it is basically checking that whatever the function you have defined, that is correct or not, right? So to verify that the correspondence of a function, we assume that, so what do? We take two elements as equal and we see that whether their images, they are also equal to each other or not. Now what does this mean? It means that you are taking two different elements, not two different elements, you are exactly taking the one element. Now if one element will give you two different images, right? So that means to say that if you have x1 is equal to x2, that means basically you are taking the same element. This is x1 and this is x2, and they are basically the same elements. So because we are taking them to be the equal elements, right? So for these two equal elements here, if you are having two different images, so that means we would have phi of x1 as one different thing and phi of x2 as a different thing. So they are not equal to each other. If this is so, then this would not be a function, right? However, if the images are also equal to each other, right, if this is the case, then obviously we are to say that in that case both the images, they are going to map onto one single thing, and that single thing would be phi of x1 also and phi of x2 also. Why? Because they are both equal to each other. So you see, we have this as the property for function, and this is how we could check it for various for the well-definedness of a certain function. Correct? Okay, now let's see that the corresponding which is defined by this phi of a divided by b, that is equal to a plus b. So here this is the rule that is defined to us. Here the mapping phi, for the mapping phi we have Q, the set of rationals, as the domain set, and Z as the set of integers as the range set, right? For that we need to check whether this is a function or not. So here in this case this is not a function. Why? Because x1 is equal to x2 does not imply phi of x1 equal to phi of x2 for all the elements x1 and x2 which are member of this rational number. How this is so? You can see this through this this statement here, because each element of domain is mapped to exactly one element of the range. This is the definition, or mathematically this is the definition for a function, right? Then in that case, here you are able to find two such elements here from the domain such that they do not have a unique image. That means that means the same elements have different images. So we have x1 as 1 by 2, x2 as 2 by 4. Now actually x1 is equal to x2, but we are just writing it in another form, right? Now according to definition, what is phi of a by b? Phi of a by b, phi of 1 by 2, that is 1 plus 2, that is 3, and phi of 2 by 4, that is according to definition it is 2 plus 4, which is equal to 6. So clearly you see both 1 by 2 and 2 by 4, they are equal to each other, but the images 3 and 6, they are not equal to each other. So that means here this is not following the property of this well-definedness of this function. So that means this is not a function, right? This is how you are going to check whether the defined mapping, that is a function or not. Correct? Now next let us move on to another concept, which is the composition of functions. So how do you multiply different functions? In order to multiply or to compose two different functions, you have to first of all see whether the range of first is the domain of second or not. They should be equal to each other. If that is the case, then only you are able to define this composition or multiplication, and this multiplication is defined in this way that you first write psi and then you write phi. Why this is so? Because suppose you take because phi is defined from A to B, psi is defined from B to C, right? So if you take some element x here, how would you solve it? Here, first of all, you will solve it for phi. So that means this x should belong to where? This should belong to A, right? And when you solve this phi of x, it would be member of B. So that means psi or whatever element y you are getting, that is now a member of B, and the domain for psi is also B. So that means you are now able to apply this phi onto the given element y, which is a member of this element C here, this set C here. So you see why this is necessary in order to define the composition of two different functions, because for the reason I have just explained to you. So the range of first should be the domain of the second one, then only you are able to define the composition, and the composition in that way is defined as the second function composed with the first function. So this is the mapping, and this mapping is now defined from A to C, because you are inputting the domain of this function phi first, and after applying phi you are getting at B, then for psi you have to have at B, and after applying this psi you are finally reaching at C. So you see we started from this A and we are reaching at this C. So this mapping psi of phi, right, this mapping psi of phi is now defined from A to C, and it is defined like this: psi phi of A is equal to psi of phi of A for all the A's which are present in the set A, right? And graphically you could see this thing like this. Suppose you have one set as the set A, another set as the set B, another set as the set C. So for these three sets, first of all the mapping phi is defined from the set A to B, right? And so if you have some element A here in the set capital A, then this phi is mapping it to phi of A. And again you have another mapping psi which is defined from B to C. If you have some element phi of A here, when you apply psi onto this, you will have psi of A which is present in C. So you see you have the composition here, and this composition is now taking this element A from the set A to C here, and this is defined here in this manner, correct? So for an example, let's consider and see this example. Suppose we have f of x as 2x plus 3 and g of x as x square plus 1. So here, because the domain and range for both of them, they are real numbers, so we do not have any issue. We may define f of g also, and we may define g of f also. In calculus, you remember, you write the composition as g o f, or you write the composition as f o g. But in our case, we can in the course further we can skip this o, and we are just writing f of g and g of f, meaning that we are composing two different functions, correct? Okay, so given these two functions and we have the range and domain defined perfectly, no issue in that. Now we are to calculate what is f of g of x and what is g of f of x, correct? So let's first calculate f of g of x. So this thing is calculated when you apply f onto g of x. And what is g of x? It is x square plus 1. So that means you have to write this g of x, that means x square plus 1, as the input into the function f, and the function function f of x is defined as 2x plus 1. So in place of x you are to write x square plus 1. So 2x square plus 1 plus 3. So when you solve, you have this thing. And similarly, when you calculate g of f here, it is first calculating f of x and then applying g onto it. So you know the definition for f of x, it is given to be 2x plus 3. So we have just replaced this f of x by 2x plus 3. Now in order to solve this g of 2x plus 3, what we have to do, in place of x Now we are to write 2x plus 3. So it would be 2x plus 3 whole square. So 2x plus 3 whole square plus 1. So when you simplify this, open up the square and then add up the terms, you have 4x square plus 12x plus 10 as the answer. So from here you can clearly see that the value of f of g, that is equal to the value of this f of g, that is equal to this one, not this one but this one, and gf is this one and f of g is this one. So you see both of them, they are not equal to each other. So I hope you understood this concept of functions. We'll be studying about more properties in the next video. Thank you for watching.